In this lecture, we will discuss the chemical synthesis of oligonucleotides, short stretches of DNA that are used for PCR primers. Oligonucleotides are chemically made by starting to add bases to a solid support. They're made in the 3' to 5' direction. Now remember, if you have an enzyme that's synthesizing DNA, that's made in the 5' to 3' direction. But because the chemistry works out better to make it in the other way, when organic chemistry is being used rather than an enzyme, they're made in the opposite direction. At the end of the process, though, the DNA will be chemically identical, except that there's not going to be a 5' phosphate on this short stretch of DNA. But that's actually useful in molecular biology because there are enzymes such as kinases that can add a phosphate onto the 5' end of the DNA, and if desired, that phosphate can even be radioactive so that we can use the primer, the oligonucleotide DNA that we're making, as a molecule to track the progress of a particular reaction. So even that shortfall has some silver linings to it. The wonderful thing about the chemical reaction is each individual round of adding a base has greater than a 99% yield. Think about your organic chemistry class and how happy you would have been to have a 99% yield in all of the reactions you did in that class. There are some chemistry things that we're going to talk about first. The first base at the 3' end is attached to a controlled pore glass bead, CPG. There's a long chemical linker that attaches this first base, whatever is on your desired 3' end of your oligonucleotide. So it has a little bit of space, so holds it away from this CPG bead. This base has protecting groups on it, as well as the protecting group dimethoxytriphenyl. Here's what that looks like right here. Dimethoxytriphenyl group protecting that very reactive hydroxyl group on our most 3' base. Then we're going to be adding phosphoramidites one at a time, depending on G, A, T, or C, depending on which base you want next. And each phosphoramidite is in turn having specific protective groups on that so that we can make sure that only the desired reaction happens. Now, a very important thing is going on in our chemical reaction. So if this is our desired sequence right here that we're going to try to make, it's actually very important that you not have a deletion in the middle of that sequence. If you happen to maybe not have the most 5' base on there, that's not the end of the world. But you really want to make sure there's no undesired changes in the middle of that sequence. Otherwise, you could potentially get your sequence binding to a wrong place on your DNA. So there are steps in there that are taken to make sure that if the next base in line, so for example, if this C does not add as it's being made in the 3' to 5' direction, if this C does not add, rather than having an incorrect sequence in here, it will allow that base to be truncated after a base fails to add. So as I said, if you have almost the same correct sequence, but maybe missing a 5' base there, your rest of your sequence will still bind properly. But if you have incorrect sequences, you run a real risk of binding to a wrong site. Also, you want to be able to separate correct from incorrect bases. And while it's possible, say you have a 20-mer, 20 bases in a row, and you're trying to purify that, you can put that over an HPLC column and you can separate maybe something that's 18 bases from something that's 20 bases. You can probably mostly separate 19 bases from 20 bases. So maybe if just the one base there does not add, and it's still the right thing, you're still probably okay. But you really don't want to have, say, something that's missing one base in the middle separate out almost the same place with something that's missing one base on the 5' end. Instead, what you want to happen is truncation, which makes it very easy to separate it on the HPLC column, because now there are very big differences in size. So here's the reaction that's happening. We start with our first base right here. So remember our first base on the 3' end that's attached with the linker to the controlled pore glass bead. It has, whatever our 3' base that we want on it, and it has that DMT protecting group. So the first thing that happens is we add trichloroacetic acid, TCA, and we do a detritylation step. This step removes that protecting group, removes the DMT protecting group, so now that reactive hydroxyl group is available. Then, in the presence of tetrazole, we add phosphoramidite, our next base in a row. We're going to skip this step for a minute. And then we have a coupling reaction. And in this coupling reaction, this phosphate right here adds on to this reactive hydroxyl group. Now we have a link between the two. So now we have our 3' most and one base that's just to the 5' end of that base. So we're making it, again, in a 3' to 5' direction. Then we have that trivalent phosphate. And by adding iodine in an oxidation step, we make it into a pentavalent phosphate. So now it's starting to look a little more like DNA, although it still has a protecting group on it. So our first step is detritylation and then a coupling step. But remember how important I said it was that if an incorrect if a base did not add, that you don't want an incorrect base to be able to add. And that's why after the coupling step, we have a capping step. Acetic anhydride is run through this tiny little column containing all these tiny little beads, and the acetic anhydride will cap off this reactive hydroxyl group if that phosphate fails to add right here. So in other words, if the coupling step does not work, then acetic acid is run through, which permanently caps right here so that nothing else will be able to be added to this base right here. So we have detritylation, coupling, and capping, followed by an oxidation step. And so then we have our two bases in a row, and this second base again has the DMT group on it, and then it goes through this detritylation with TCA to remove this DMT group right here, and it goes through this cycle a multiple number of times, adding one new base in a 3' to 5' direction each time. So after it has gone through this the requisite number of times, then we want to get rid of all of these protecting groups. We want to get rid of the DMT group that's protecting this reactive oxygen. We want to get rid of this protecting group that's protecting the phosphate. We want to get rid of the protecting groups that are protecting each of our bases. So what happens is we add ammonium hydroxide, and this removes all those protecting groups, and it causes our oligonucleotide to fall off the column and elute off of our column. So basically, here are the 5 steps: the detritiylation, the addition, the capping, the oxidation, and the deprotection step. The 5 steps of the phosphoramidite chemistry of making oligonucleotides, and the chemicals that are used in each step: the TCA, the tetrazole, the acetic acid, the iodine, and the ammonium hydroxide, and a short description of what is happening in each step. Companies in San Diego hire people who know these steps. There are a number of companies in San Diego, IDT as well as several other companies, whose job it is to make oligonucleotides for use in the biotech industry. IDT has branches in Iowa as well as California, and they make tens of thousands of individual oligonucleotides each day and ship them all over the world. And it's a very good starting job for people who are, biochemists who know this type of thing. So if you go for a job in one of these type of companies, make sure you review all of these steps.